Good day. This lesson is about gradient vector fields. I will provide you additional examples of sketching gradient vector fields. This is example number 2. So in here, we're going to find f of xy equals gradient f or del f, given the function f of xy equals x plus 2y, and sketch it along with the contour map of f. So first thing to do is to define the vector field or gradient vector field f of xy, which is denoted as del f or gradient f. So we have here now again the given function or surface is f of xy equals x plus 2y. Defining now the vector field or gradient vector field f of xy, which can be found by taking the gradient f, and that is taking the partial derivative of the function f of xy with respect to x, then with respect to y as its component. So in here, when we are to take the derivative of the function f of xy with respect to x, so taking y as constant, so the first component will be 1, and then taking the second component, that is getting the partial derivative of the function f of xy with respect to y now, and having x as constant. So we have here now the derivative of x is 0 plus the derivative of 2y is 2. And in here, we're going to define now the contour map of your given surface, which is f of xy equals x plus 2y. So what we will do is to set f of xy is equal to k. And this will be equal to, you have x plus 2y as our f of xy is equal to k. So let us define some k values. So suppose we have k value, let's say 0, your equation will be x plus 2y equals 1. When we are to describe the graph of this equation, it is a line. And defining now this slope, so defining the slope of a line, let us recall. So recall the equation of a line. So we have y equals mx plus b. So here, in our first equation of a line, so we have here x plus 2y equals 1. So we can express y in terms of x. This will now be 2y equals 1 minus 2x. And solving for y, this will now be equal to 1/2 minus x. So in here, our slope is -1. And the y-intercept is defined by b, which is now 1/2. So if we're going to sketch now the line here with the equation x plus 2y. Okay, so let us now graph x and y axis. Or let us draw the x and the y axis. Then let us now plot the y-intercept as well as the slope of your line, which is x plus 2y equals 1. So the y-intercept, so it is a point on the y-axis at 0, 1/2. And that is the point now, we'll measure for the slope since it is rise over run. So we measure first run, which is -1, then up, which is also 1, but it is +1. So from here, we can now connect these 2 points. So this forms now your equation, or rather your line, which has the equation x plus 2y equals 1. Then if we're going to assign now, by the way, this is when k equals 1. Sorry for that. Then when k equals 0, so we have x plus 2y equals 0. Then solving for y in terms of x, so y equals, now have -x over 2. And with that, by the way, I also committed a mistake here. This should be x only. Okay, so therefore this should be x over 2. So nevertheless, so the slope is -1/2. Then this is your y-intercept. Okay, so nevertheless, this is still the graph of the line which leans to the left.
It's 21 hours.
Then we now have here x plus 2y equals 0 at k equals 0. So with that, defining now the slope is also -1. Then the y-intercept this time is 0. So the y-intercept is at 0. Then for the slope, we count 2 units to the left and 1 unit upward. Then let us connect these 2 points. So connecting all these 2 points, we now have a line parallel to the first line. So we can generate similar lines. And even if we're not going to get anymore the other equation, so we can just generate these lines. So just take note that they are parallel, and of course they have the same slope. So these are the lines that can be formed from the given equation x plus 2y equals k. So it is a set of lines, slant lines particularly. So this comprise the contour map of your given function. And if we're going to get now or if you're going to draw the vector that is orthogonal to the contour of your contour map of your function f, so this can be obtained by having these components of your gradient f, which are both constant. So at any point here, we now have, let's say at 0, so we're going to measure 1 to the right and 2 upwards. So that is representing the vector 1, 2. So you now have, let's say this is now 1. So let us just estimate that this is 2. Then we just connect the 2 points. So let me use another color. So distinguish it from the lines. Then let's have another, let's say at this point here, So you measure 1 unit, then 2 units upward. So we do the same here. So let's say you can just select any point. So let's say this is your point, then 1, then 2. So of course, the length of the vector are increasing. So the direction of your vectors is going upward to the right or in the right direction. So we can just now follow the pattern. So these are the vectors orthogonal to the contour map of the given function. So you can continuously graph it. So don't worry about the magnitude because even if it is, as you can see, there are vectors which I draw not to scale. So you can use a software like Matlab to check the correct, or I should say accurate, representation of the vectors that are orthogonal to the given function. So let us check the solution using Matlab. This is the solution provided by using Matlab. So as you can see, it's almost similar to what I have drawn or sketched. And it says here the vector field f of xy is gradient f equals f sub x, f sub y equals 1, 2. So these are also the same values that I have obtained a while ago. Then the surface of f is a plane tilting upward as x and y both increase in value. So in other words, we have now the contours of f are all line of the form x plus 2y equals k, or y equals negative 1 of x plus k over 2, and that the vectors in f are orthogonal to the contours of f, pointing in the direction of increasing z.